Welcome to episode 46. Today we're tackling a fascinating paradox. Stability isn't about raw speed. It's about mastering uncertainty. In the world of logistics and transport, we're all chasing efficiency. We want things faster, cheaper, better. But have you ever noticed that the faster you try to make a system, the more fragile it can become? One small hiccup and the whole thing grinds to a halt. I've seen teams spend months optimizing every millisecond out of a process, only to have it completely fall apart under real-world pressure. They were so focused on the best-case scenario that they forgot to plan for the inevitable chaos. That's because true stability doesn't come from just going fast. It comes from having a plan for when things go wrong. It's just about designing a system that can handle the unexpected, a system that anticipates failure and knows how to recover gracefully. So let's redefine our goal. Instead of just chasing speed, let's learn how to build systems that are truly resilient. To understand this better, let's use a simple metaphor. A logistics company delivering packages. Think of our system as a fleet of delivery trucks. Now, let's introduce some stability mechanisms. First, we have a timeout. Imagine you send a truck out, but you tell the driver, if this package isn't delivered within 3 hours, forget it and come back. Because maybe the customer isn't home or the address is wrong. Instead of letting that truck get stuck all day, you set a limit. You accept a small failure to protect the rest of your operations. That's a timeout. It prevents one problem from tying up valuable resources indefinitely. Next up is the retry mechanism. What happens if a truck breaks down on the way to a delivery? The delivery fails. A simple system might just stop there. But a stable system has a retry plan. The dispatcher immediately sends another truck with the same package to complete the delivery. It might be a little delayed, but the customer still gets their order. We're acknowledging that failures happen, and we're building in a process to try again automatically. This simple act of retrying can be the difference between a minor hiccup and a complete service failure. Now, what if the main highway is completely gridlocked with traffic? This is where degradation comes in. Instead of forcing all your trucks onto that congested route, a smart system says, okay, the main route is compromised. Let's switch to the backup plan. Maybe you start using smaller, local roads. The delivery might take a bit longer, and perhaps you can't carry as much in one go, but you're still moving. You're degrading the service gracefully, offering a slightly slower but still functional experience instead of a complete standstill. You're accepting a lower level of performance to maintain availability. Finally, we have the most powerful mechanism, the circuit breaker. Imagine one of your main distribution centers has a major problem, say, a power outage. If you keep sending trucks there, you'll create a massive pileup. Packages will get lost, trucks will be stuck, and the chaos will spread. A circuit breaker is like a manager on the scene who says, stop, don't send any more trucks to this center for the next 30 minutes. You temporarily close off the broken part of your system to prevent a cascading failure. This gives the distribution center time to recover, perhaps by switching to a backup generator. After the 30 minutes, you send a single test truck. If it gets through successfully, you close the circuit and resume normal operations. If it fails, you keep the route closed and try again later. The circuit breaker protects the entire network from a single point of failure. So, what's the core insight here? Reliability isn't an accident, it's engineered. Whether we're talking about logistics networks, computer networks, or any complex system, the individual components are inherently unreliable. Trucks break down, roads get blocked, networks drop packets, servers crash. You cannot optimize your way to perfect reliability by just making one truck faster or one server more powerful. It's impossible. Stability doesn't emerge from a single heroic effort. It is the direct result of deliberately engineering these mechanisms, timeouts, retries, degradation, and circuit breakers into the very fabric of your system. You have to assume things will fail and design for it. This is a fundamental shift in thinking. Instead of praying for the best-case scenario, you plan for the worst. That is how you build something that is truly robust, something that can withstand the chaos of the real world. Stability is not an attribute you have. It's a capability you build. Now, as we start giving our AI systems the ability to use these tools to automatically retry a failed order, reroute a delivery, or even trigger a circuit breaker, we run into a fascinating new problem. It's a trust dilemma. To make these systems autonomous and resilient, we need to give them more permissions, more power. An AI that can automatically retry a failed transaction also has the power to place 1,000 rogue orders if it misunderstands a command or encounters a bug. When an AI can independently call different tools and services to solve a problem, who is making sure it's making the right calls? Who ensures it doesn't accidentally trigger a system-wide shutdown because it misinterpreted a minor error? As we move towards more autonomous AI agents, the question of security, control, and governance becomes paramount. We'll be diving deep into that very topic in our next discussion, exploring how to build guardrails for these powerful new systems. Make sure you're subscribed so you don't miss it. Thanks for watching.